Welcome to the Prosthetics and Orthotics podcast with Brent Wright and Joris. Hello everyone, my name is Joris and I'm here with Brent Wright on the Prosthetics and Orthotics podcast. Hi Brent.
Hey Joris, good to be on this podcast today, and I'm really looking forward to who we've got lined up.
Okay, because you brought us somebody who's he's orthotist, prosthetist like you, right? And somebody who you described him as a real craftsman who's also a digital craftsman, and he does a lot of work in upper extremities and stuff like that, right?
That's right. Yeah, and I'm just really excited to have him share a little bit of his journey and maybe a little bit of insights into some of the solutions that he's found. He's probably not going to give us much into the stuff that is kind of intellectual property stuff, but maybe outline some of the things that he does or the way that he thinks. And so I think that's going to be a big benefit to us.
Okay. All right. So with that, Chris Baschuk, welcome to our podcast.
Thanks, Joris. I really appreciate you and Brent inviting me on here today. I'm looking forward to our discussion.
Okay, good. All right. So first off, right now you work for Handspring, right?
Yes, that's correct.
And you why did you end up with, of all the directions you could go in, why specialize? Well, first off, why specialize at all? Is it important to specialize? Is it kind of something that you felt was necessary, or?
Yeah, it really is. I think that specialization is going to be a critical component in the future of orthotics and prosthetics. When I went to prosthetic school at UT Southwestern Medical Center in Dallas, Texas, I knew immediately that I wanted to focus my career on upper limb prosthetics. I just find hands fascinating, the things that we can do with them, all of the different degrees of freedom that our hands have, and being able to try and replicate that and help individuals who've lost that ability just really resonated with me. And so I aligned myself early on in my career trying to make connections with other individuals who had already gone down that pathway, people like Chris Lake and Pat Prigge in the United States, who I just looked to as real visionaries and creators, and got connected with them. And that led me down this path towards Handspring. Anyone who wants to go into orthotics and prosthetics has to go through their master's degree education in the United States, and then they have to do a residency. And in your residency, you are a generalist, you cover all the basics, but most practices don't enable you to be able to see a sufficient number of patients with upper limb involvement to really become proficient with it. It's something that you truly have to seek out. The standard O&P practice is going to see 95 to 99% lower extremity and only 1 to 5% upper extremity. So if you want to specialize in upper extremity, you really have to seek it out, and you have to do that through collaboration with others, because our current educational model doesn't really provide the education that you need in order to understand how to take care of individuals who need upper limb prosthetic rehabilitation.
Okay. I mean, and so, yeah, first of all, the hand does seem like a particularly complicated thing to kind of try to replace.
Absolutely. Yeah, I like to say that we use our hands to interact with the world, and we use our legs to get around in the world. And it's two entirely different paradigms when you're talking about how to get around in the world and how to interact with the world.
Mm-hmm. Yeah. And where are the difficulties when trying to make it? Is it just that it's a really complex thing, or that it needs to be really very precise, or where are the problems really?
The challenges really relate to each individual is very different. How they want to interact with the world, how they interacted with the world prior to their injury is very different from individual to individual. And so you have to be able to be really creative, and you also have to be able to develop a really good relationship with that individual so that they trust you to be able to really explain what they want to do in this world. And then you have to have kind of a large quiver of ideas on how you could go about to address that. And then you have to be able to implement it. And that's one of the challenging things, is a lot of the time they want to do things that others haven't ever done before. So you essentially have to prototype and R&D a solution for them every single time. It's not just a matter of, I want to walk around. It's, I want to play the piano. I want to play basketball. I want to be able to write. I want to feed myself. These are all different things that, each individual brings to the table, and you have to be able to be ready to meet those with the available resources that you have.
Okay. And then, and so really you would also like what Brent mentioned before, you would kind of look at the person's lifestyle when designing this prosthetic. Is that a really important thing as well?
Absolutely. That's fundamentally critical. And I think when prosthetists don't do that, that's when they end up missing the mark and end up producing a prosthesis that may look cool, but might not actually function and do what the individual was hoping that it would.
Yeah. And why is that important? I mean, I think, so if someone would be outdoors a lot, it has to be better against water, is like practical stuff like that, or?
Yeah, absolutely. So, I mean, imagine if you're going out to go hiking and somebody handed you a pair of dress shoes to go do that in, right? That wouldn't be appropriate and wouldn't help you. And so then ultimately you would set those dress shoes aside and maybe wear the tennis shoes that you currently have instead of the hiking boots that you really needed to go on that journey. And that's what happens a lot.
Mm-hmm. Okay. And so typically, I mean, I could imagine this could be really low tech as a solution as well. You could have some kind of hooky type of mechanical thing, or you could have a full myoelectric kind of robot type of thing going on. What do you do exactly?
Depends on the individual. I do both. And I think that's a pitfall that comes sometimes too, is a lot of my initial interaction with a new patient is setting realistic expectations and kind of walking them back from what they may have seen in marketing videos on YouTube, because those videos that are out there, show a very specific action that somebody's doing, and it's really amazing what they're being able to do with the prosthesis. But what it doesn't show is, the 2 hours of footage before that of the individual trying to do that one thing that one time in order to get that one, slick marketing video. So I have to work with them a lot to do that, because there's a time and a place for each type of prosthesis, and it's a matter of what they're really trying to accomplish. And sometimes prosthetists kind of fall into this pitfall of what's called the appeal to novelty, where they think that the newest, latest, and greatest technology is going to solve all of their problems. It's going to be a panacea, and they rely on the technology to solve their problems rather than their own clinical judgment and skills.
Mm-hmm. Okay.
Chris, just wondering, what would you say is kind of like the lowest tech prosthesis that you've delivered that has had a high impact? And then I'd love to just ask you the flip side of that too, the highest tech prosthesis that you had that's also had an impact. Just sharing with us kind of the range of what you do.
Absolutely. I mean, if you want to think super low tech, just a small little silicone finger that just adds maybe a centimeter of length to somebody's finger because they lost part of the very end of their finger, but you add that little extra length, and and we've even made them touchscreen capacitive so that they can reuse, like their index finger, for example, just to touch a screen and not have to move their wrist and their arm in a different way than they would. I mean, it's very fundamentally basic, but it changes somebody's life. And the real sad thing about that is something so fundamental and basic like that is so hard to get an insurance company to actually pay for. And that's a whole nother soapbox that we could go on at some point, but I won't belabor that point right now. To answer your other question, Brent, something more advanced, anytime you go further up the arm, you're adding more components and more complexity into the whole system. So, I mean, you can get somebody who's missing their arm all the way up to their shoulder, including their scapula. We call that a 4/4 level amputation. And so you've got to replace their shoulder motion, you got to replace their elbow motion, you got to replace their wrist motion, and then their function with their hand. And so there was one prosthesis that I was involved in that utilized what we call a pattern recognition system to be able to control all those different degrees of freedom. And it was really interesting because he was an individual that had that high shoulder level, sort of an amputation. And when I tried to test him to see if we could get any sort of EMG signal, which is, surface electromyography, where we put an electrode over the muscle belly, and as they fire their muscles, it picks up that micro voltage and then amplifies it and tells the prosthesis to move. Well, in his case, I couldn't actually get that with our traditional types of signals. So we use this array of electrodes, of 17 electrodes, and putting that system on him enabled us to be able to ask him, visualize moving your shoulder, or visualize moving your elbow or your hand or your wrist. And as he visualized doing that and contracted his muscles, we were able to actually pick up discrete muscle contractions that then we were able to program the prosthesis to do that function every single time that he repeated visualizing that sort of emotion. And so, life-changing. He now has the capacity to use his arm again. It's not fully functional in the way that his other side is, but it's sufficient to be able to be a helper and a support, so he can offload some of the use of his sound side. Because that's the biggest problem, is that people become unilateral after they have an upper extremity amputation. And most people can do everything that they want to, honestly, with one hand. But the problem is that as they start to do that, then that hand or arm ends up getting worn out prematurely. And so the purpose of an upper extremity prosthesis is to help balance that out, so that they're being able to use bimanual tasks, or using both sides of their body equally again, so that they're not wearing one side out or the other prematurely.
Mm-hmm. And then so we got on the one hand, you've got a pretty there's a couple things you're touching on all at once. so let's just talk about like the types of prosthetics here. You've got a really simple thing, which I'm thinking is just like, are we talking about like this is a piece of silicone? That's literally what we're on, the really simple.
It's just a little cap of silicone that's custom molded to the end of their finger, so it stays in place via suction, essentially. And it's very, very basic. Just a little glob of silicone on the end of their finger that's been custom molded to them. Yeah.
Okay. And then what's like a more high tech kind of version? What's the next step up, let's say?
So we've done the same thing, but with actually 3D printing. So we will scan their other hand and make a mirror image of it, and then we can use whichever fingers are missing. We can use that as a basis to then design a 3D printed finger that goes over their residuum, their residual digit there, so that it looks more anatomical, and then also assists by increasing that length. We can use that same sort of a scan, and then we'll hand it off to an artist who will actually hand paint it, made it out of silicone, to match their skin tone and texture and hair and freckles and veins really precisely. We call that a high definition silicone restoration. So that would be the next step up from that. But very different uses, very different use cases for those. The silicone ones are not going to be nearly as durable, but they'll look the most lifelike, whereas the 3D printed or just the basic silicone is going to be more durable and for different environments.
Yeah. And so so the hooks, it seems like that would be like the most ancient solution ever, and then we're way past that, but still people have these hooks and things. And is it just really handy, or what's the idea?
Yeah. So hooks are an interesting thing. I mean, they have been around forever. And it's had a pretty bad stigma in the past, but as you work with an individual and show them why it's functional, it makes a whole lot of sense. So one of the biggest challenges when somebody loses part of their hand is that they also lose their sense of touch. It's one of our 5 senses, and it's really incredibly important for us to be able to utilize. If you think about it on a daily basis, when you go about your life, you don't have to look at what you're doing a lot of the time, because your hands with your proprioception know where they are in space, and they can tactily feel what they're grabbing onto. Well, you lose that, if not completely, depending on how much of your hand you've lost when you've had a traumatic amputation. And so you have to be able to augment and supplement that loss of touch with one of your other senses, which most of the time is visual. So you actually have to look at what you're doing and be more focused on it than if you were not using a prosthesis. So when you think about it, if you look at the back of your hand and realize when you go to grab something off of the table, for example, like a pen or a pencil, or maybe even like a quarter, if you do that the normal way, you're watching what you're doing, you realize that you're staring at the back of your hand the entire time, right? And you can't see what your fingers are doing when they're going to pick that object up. So that's the same thing with a prosthesis. If you have a prosthetic hand, a terminal device that looks like a hand, and you go to pick something up off the table, you're going to have to move your whole body to the side and look at what you're trying to grab. With a hook, the hooks are designed, it's not just a passive hook. It actually has two tines on it that when you pull on a cable, it opens up and it actually is able to grab onto things. And when it opens up, because they're just these two little narrow tines, you have a clear field of view of the object that you are trying to pick up. And because they're tines and they come down to a pretty fine point, you're able to actually pick up really small things, even like a pen or a needle off of a table with that, because it comes to such a fine point there. And so it really is quite a functional device in that regard. I kind of like to equate it to a standard light switch, right? I mean, there are fancy light switches that integrate with our home electronic systems now and do all sorts of crazy things. But fundamentally, the underlying function of it is just it turns a light on or off, and it's just a basic switch, right? And that aspect of it hasn't really been innovated on much. It's the same with these hooks. They really do just kind of work. And it's always a good backup device to have, because these more advanced technologies that we have available to us now require more maintenance, and sometimes they have to be sent in to the manufacturer to get repaired. And so providing somebody with a basic hook style prosthesis, something that we would call body powered, it doesn't have any electronics in it or anything, is really something that's essential, so that they always have a backup, something that they can turn to, so that they're not losing the functionality of that upper extremity completely if something goes wrong with their device.
Mm-hmm, mm-hmm. And there's also something I saw that was it's called Jaws or something, and it looks like very much like a Bond villain might have it, and it kind of like closes and stuff.
Yeah, that's a really great new terminal device. So every time we talk about something that's at the end of a prosthesis, we refer to it as a terminal device, as the broad general category. So the Jaws terminal device was invented by a good friend of mine, Bob Radosi, who has a company called TRS Prosthetics out in Boulder, Colorado. And Bob developed that as a terminal device that could be used with a traditional body powered system, cable driven, or you can take the whole cable off and not need it. And when he designed it, he was looking at those little toys that have the stick that you pull on the trigger, and it closes the mouth of like a little shark mouth. So that's where he actually got the inspiration for that terminal device a little bit. So he intentionally made it look like it's kind of got a dorsal fin on the back of it, and whatnot. So, but yeah, that device is a really robust terminal device. You can use it for things like going on a bicycle, or on an ATV, or a motorcycle, or on a jet ski. Or you can use it for pushing your lawnmower or a shopping cart. It's really versatile in its functional use. One of the great things about it, it's got this lever on it so that you can control the tension of the spring that keeps the jaws of it closed. And so if you really need to hold on to something really strongly, you can flip that lever forward, and it will really kind of lock on. It'll still at some point be able to break away, because you don't want to generally ever permanently connect somebody to something else should an accident occur. But yeah, that's a really cool new device that's just come out in the last couple of years.
Mm-hmm. And then also, okay, so we've got these terminal devices. Are there any more terminal devices? Well, then there's like the myoelectric hand kind of thing, right? Or
yeah, I mean, so Bob's company TRS makes a whole wide variety of what we call activity-specific terminal devices. They are devices that are used for one purpose primarily. So, for example, he's got a a hoop that's designed for helping play basketball, or an attachment to hold onto a ski pole, or a hook to go rock climbing, or this one called the lamprey that's designed to hold on to the forestock of a firearm so you can enjoy shooting sports again. You name it, he's got a design for that. And then there are others, another company called Texas Assistive Devices that make more utilitarian type attachments, where they essentially will weld the attachment to the prosthesis to whatever tool that you could imagine, be it cutlery, or knives, or wrenches, or fishing poles, things like that. So yeah, there's a whole lot. And then with additive manufacturing, if somebody wants to do something really unique, we can design it for them and print out a custom terminal device just for them for whatever activity it is that they're wanting to accomplish. And that's really fun.
And these custom things are mostly related to activities where, like, maybe the really high-tech hand will not be robust enough. Is that really the thinking here, that if you use that for archery, it would get wrecked? Or yeah, that's a perfect example. I know there was a Super Bowl ad a couple of years ago that showed an individual using their bow and arrow with a myoelectric hand, and that works great for a couple of times. But long term, if somebody's really into archery, that's not going to be the best choice of a terminal device for them. Mm-hmm. Okay. Yeah, it probably look cooler, right? Yeah, that's
right. It looks way cool. Yeah. Angel was the individual in that Super Bowl commercial, and yeah, she makes prostheses look really cool.
That's good.
So I had a question for you, Chris, on the for when you're talking about a prosthesis and kind of having symmetry. I mean, is there ever a time where you say, you know what, it's probably better to go, the best prosthesis is no prosthesis at this time?
Absolutely. Yeah, that's a really great point. And that's something that I do cover every single time that I meet with someone. There is a time and a place for a prosthesis, and there's definitely a time and a place to not use a prosthesis. And it's really important, outside of the scope of prosthetics and orthotics in occupational therapy, that once you've provided the different prostheses to the individual, that they get connected with an occupational therapist who can show them how to use the prosthesis, but also show them how to do their ADLs, their activities of daily living, without a prosthesis. And a good friend and colleague of mine, Debbie Latour, has a whole series online that teaches occupational therapists that whole paradigm. She goes through this series of videos where she shows how to use a body powered prosthesis to do something, how to use a myoelectric prosthesis to do something, and how to do that same thing without a prosthesis. And it's really important that we educate our patients on those three ways of doing things, so that no matter what circumstance they find themselves in, they don't feel unable to do what they're trying to do.
Yeah. I think that's interesting. Okay, so then we go to like the myoelectric hand, which sounds like the be all end all. We already have a little bit of a qualification, a little bit of stuff there that may not be. And how does that work? That sounds like a really high tech solution. Let's say.
Yeah, I mean, it is an advanced solution, and we've gotten to the point now where there's 25 different of these myoelectric hands or so that are on the market or coming to the market in the next year or two, and they all run primarily on the same principle, that we use some sort of a sensor, whether it be a strain sensor that is put into a harness that you can tell the tension on it to, or be it surface EMG with myoelectrodes where we're picking up the signals from their actual muscles. They essentially tell the terminal device to open and close. And that has been the way that those types of devices have functioned since the concept was initially developed in the 1950s.
Well, how does that work? Do I think open or something, or how does that work?
So imagine, so let's just say you've lost your hand and you still have the majority of your forearm, right? So you still have all of those muscles in your forearm on the one side, on the palm side, you have your muscles that all work to close your fingers. And on the other side, the back side of your hand, you have all of the muscles that open your fingers. So most people don't realize, but the muscles that actually control the movement of your fingers are not necessarily in your hand. They are actually in your forearm. So if somebody loses their hand, they still have all those muscles in there, and they're still all alive. They're just not connected to the fingers anymore. So if you make a contraction, say you in your mind still make a fist, all of those muscles on the palmar side of your forearm are still going to contract. And when you think open my fingers, all of those muscles on the other side of your arm are going to contract. And so if we put an electrode on one side, on the closed side for making a fist, and another electrode on the opposite side of the arm to open the fingers, then when you make those muscle contractions, that your muscles work through electrical activity. And that little sensor on your skin actually can sense that there's electrical activity there, and it takes that information, it sends it to the prosthesis, and it activates the motors to either open or close the hand. And so it's just a two input sort of a system, open or close. And that's how functionally all these hands work. Even if they've got individual fingers that can move, as it stands right now, using technology that's commercially available, we can only tell it to open and close, essentially, in whatever posture or grip that the hand is in. So for example, these hands that have multiple motors in them, you can tell the hand to toggle into a specific grip. So let's say we would call it a pinch grip. So the middle, ring, and little fingers are closed on the hand, and then the index finger and the thumb are the only ones that are going to be active, and they can pinch together on each other and open and close, and that sort of a grip, we would call that a grip. You can imagine a different grip where all fingers, index, middle, and ring, and little, are all closed in sort of a fist, and then your thumb is out to the side in a kind of a thumbs up position, and then you can close the thumb down onto the index finger in what we would call a lateral grip. So that's a different style of grip. And so these hands, some of them have like 32 different grips that they can be put into, and then they just open and close in that specific grip based on the inputs from those electrodes that are on it.
Mm-hmm.
On the skin.
I was reading about something called like pattern recognition software or something. It's supposed to like be like the next thing in that, or is that different, or is that kind of basically what you've been saying already? Right?
So that's the next evolution. So with pattern recognition, instead of just having the two electrodes, you can have an array of electrodes, be that as few as 4, but up to 32 channels or even more, quite honestly. And instead of just looking at is the muscles under one electrode active to close, and are they active on under another electrode to open, it's essentially making a whole map of the electrical activity in the forearm. Because as we do different grips with our own natural hand, different muscles are functioning, and so there will be a different pattern of electrical activity in the forearm based on the type of grip that you're visualizing doing. And so pattern recognition harnesses that ability to distinguish between those different electrical activity patterns. And then it takes that information and it classifies it, and it says, for example, it looks like they are pointing their index finger. So then we program the prosthesis to recognize that every time it sees that sort of a pattern, it tells the prosthesis, point the index finger. And so that's where pattern recognition can be really valuable, so that instead of having to toggle through a whole bunch of these 32 different grips to try and find the one grip that you're actually wanting to use at that moment, pattern recognition unlocks the potential for an individual to be able to directly access that specific grip by doing a specific contraction in their arm. And it takes practice. It's not just immediately they can always consistently do that, because they have to consistently do the same sort of contraction every single time in order for the prosthesis to move the way that they want it to move. And there's been some really good advancements with that technology, with AI even being integrated in the background to be able to adapt, because as you use your muscles throughout the course of a day, they do fatigue. And so their electrical activity does change depending on how much you use those muscles. And so the patterns can kind of mutate and change throughout the course of the day. So, the technologies that have been integrated into these systems in the back end can see those changes and help adjust the algorithm that's going on in the background to make sure that the prosthesis does what the individual is intending for it to do and not something else.
Mm-hmm. Well, and so also then this is a really expensive solution, right? We're talking like tens of thousands of dollars, right? Or
yeah, we are talking about tens of thousands of dollars. For example, a full transradial level prosthesis, something that's below the elbow, with all of these different components, talking about a multi-articulated hand with multiple motors and a powered wrist rotator and a co-op pattern recognition system integrated into it. Something like that costs on the order of $100,000 or more. And a lot of that is hard costs of the componentry itself, because there's a lot of research and development that go into making these technologies, but in the reality of the marketplace, it's a very, very small market. So within the United States, for example, there are 2 million individuals living with some form of limb loss. And of those 2 million, only about 10% have any sort of upper limb loss. And of that small 10%, only 10% of those have any sort of an amputation that is a higher level than just the wrist. So it's a very tiny market with, it's really high cost to R&D these products. So the cost of purchasing the product, since there's going to be so few of these parts sold, is going to be pretty high. A prime example, in the news in the last years, there's all this talk about the Luke arm, this prosthesis that the Department of Defense in the United States helped fund and create. And they spent an exorbitant amount of money on this. Some say it was over $100 million on the entire project to develop this one specific prosthesis that can, move in a whole bunch of different ways. They have sold 20 of those in the entire world since that project. So $100 million to sell 20 products so you can't ever recoup that. And then the other part, with the way that prostheses are paid for in the United States, is that we as a prosthetist are not able to bill for our clinical time. And so we're expected to care for an individual for 3 to 5 years for the lifespan of that prosthesis. That's how long that whole episode of care is. But we essentially get to put a bill to the insurance company or to the patient once during that whole process. And so that whole episode of care the cost has to be kind of front loaded into the overall cost of the prosthesis. So when you start to understand it that way, you understand why they do cost so much. And that's something that I see, misconstrued in the media all the time. There's this whole article that's always been cited as saying, a girl was fit with an $80,000 prosthesis and it never worked. And so then somebody 3D printed a prosthesis for her that only cost $30 in materials, and it worked just as well as the $80,000 prosthesis for her. I mean, there's so many different things that are wrong with that comparison, but it's something that in the media is consistently repeated because it's a shiny, sexy headline, right? Oh, well, why are people spending $80,000 on prostheses when they should only have to spend $30 on prostheses? It's just an inaccurate comparison.
Mm-hmm. Okay. And just before we're looking a little bit more into the technology available now. I mean, we've also got elbow kind of joints essentially, right?
Mm-hmm. Yeah.
Like, what do these do? Because there's different motion systems, right? There's kind of a motorized and a cable, and there's all sorts of things going on, right?
Yeah, exactly. So fundamentally, There are a couple of different classifications of prostheses. We have, as Brent mentioned before, no prosthesis. That's one option. The next is a body-powered prosthesis, something that is using cables to provide, translates the physical motion of the body into a mechanical motion of the prosthesis through a cable system. The next is an external powered system, or myoelectric, sometimes you hear, or bionic prosthesis. This is something that uses electrodes or sensors to power motors and move a prosthetic joint through that method. Then we have activity specific prostheses, which we kind of touched on with the different types of attachments that you can have for them to do a really narrow focused task. And then we have what we call passive functional restorations. Some people refer them to them as cosmetic prostheses, ones that are meant to look more lifelike than anything else. So those are the primary kind of classifications of prostheses that exist. And then you can go into what we would call a hybrid device, where part of it might be powered by motors and the other part might be powered by body power. So for example, a good example of that is sometimes for people who have an amputation above the elbow, we will power the elbow joint with a cable because it's a very robust, easy, quick method of powering an elbow. But then the terminal device may be an electric terminal device. So it's a hybrid of the two. And that can be really functionally beneficial and also cost beneficial, because a powered elbow costs on the order of $40,000 just by itself. So it's an expensive, heavy component that is very functional for the right individual, but it's not right for everyone.
Mm-hmm. Yeah. And then you've also got like these flexion wrists and all these other different types of wrist parts as well, right?
Yeah. So, our wrist can do a whole bunch of different things too. It can rotate, it can flex, it can extend, it can deviate from one direction to the other. It's an artificial ball joint in the sense that it can circumduct and go in all different directions. And so with a prosthesis, every time you want to replicate one of those degrees of freedom, you have to have a different control system and motors in place for it. And so there are wrists that rotate, there are wrists that do bend, and there are some body-powered wrists that do both. What's nice is that some of the manufacturers of, going back to these bionic hands, they've started to actually integrate the ability to flex and extend the wrist into the hand itself, so it doesn't add any extra length to the whole prosthesis. And then we can use a wrist that has a motor in it to be able to rotate it. And all these devices too, I don't think we've touched on this, they're interchangeable. So you can have one prosthesis with the socket that goes over your arm, and then they have quick disconnects so that you can swap out the terminal device for a different terminal device depending on what it is that you're trying to do.
Mm-hmm. Mm-hmm. Okay, that's cool. And then you also have like the actual arm bit, right? Which is just like basically looks kind of like a relatively dumb bit compared to like if we're looking at the forearms, let's say, compared to the other ones,
Right. So you're talking about the part that goes over the person's body, right?
Yeah, exactly.
Yeah. So we refer to that as the socket, and it looks dumb, but honestly, it's the most important part of the whole prosthesis because it's where the human body interface is. And if that is not fit properly, it does not matter what sort of attachments you put onto it, it's never going to function for the patient. And so that in particular, going back to the very beginning of our conversation where we were talking about specialization, that's one of the most critical differentiators between lower extremity prosthetics and upper extremity prosthetics. If you think about somebody walking around, right, when they're walking, they're, for the most part, the majority of the time, they are standing on the prosthesis, and the prosthesis is there to support them. Well, the opposite is true for upper extremity prostheses. Almost 100% of the time, the prosthesis is hanging off of their arm. And so the mechanics are entirely different, and the principles of socket design are entirely different when you're thinking about having to suspend the prosthesis versus having to have the prosthesis support the individual. And so that's one of the areas where, if you have a prosthetist who doesn't have an extensive amount of experience in fitting an upper extremity prosthesis, and most of the time they only fit lower extremity prostheses, they just aren't going to have the experience to know the changes and adjustments that need to be made to that socket in order to make it fit and function the way that they desire.
Mm-hmm. Mm-hmm. And we also have like stuff like IntelliSkin and stuff like this, which is like kind of like a silicone liner for over it or something like that, or how do I?
So you can have custom coverings made for the prosthesis that are made out of silicone typically, and I think you might be referring to something that's kind of being researched right now is a skin that can actually produce that sensation of touch again and send that back to the prosthesis, so that the individual can have that proprioception restored to them. And yeah, that's it's nothing that's commercially available at the moment, but it's one of those technologies that's really exciting to know that it is going to be able to come. As it stands right now, pretty much prostheses are the communication between the person and the prosthesis is a one-way street. The person is sending information to the prosthesis, and the prosthesis does something. We aren't at the point where the prosthesis is able to send information back to the patient and their central nervous system. But that's
and
something that.
So how do I know when to grip a glass exactly? This seems really, I've never understood this. Like, how do I know when I'm actually holding the glass, and how do I know when I'm about to crush it? That kind of thing.
Right. So if you were using a prosthesis, you have to rely on the prosthesis to process that information internally itself. So a lot of these hands, they have what we call an autograsp technology in it, where they close down, and as soon as the motors recognize that they're getting some resistance, they slow down and stop, so that they don't crush something. And then you as the user have to send an additional close signal to the prosthesis by contracting those muscles to then have it close down a little bit tighter. And you can pulse that. You can keep going close, and it will just slowly close down tighter around whatever object that you are grabbing. And to a point, right? These are not Terminator hands that are going to crush objects anymore. They do have limits on the grip strength that they have, but that's how it works. And so then they're smart enough that they can sense if an object is getting loose in the hand and it's starting to slip a little bit, and they'll tighten down on it to prevent it from slipping until you, as the user, send an open signal to open. The other thing that on the back end, what people don't see is, as a prosthetist, you have to go in and adjust a whole bunch of different settings to fine tune the signals that the prosthesis is receiving, because every person's muscles are a little bit different. Some, if you want to think on a volume scale, some are louder than others, when they're active. And so we have to adjust the gains and thresholds, the points when we tell the prosthesis you're turned on, and then the points where we tell the prosthesis you're turned off. And then we also have to there's kind of a window of control, so that when you have a smaller muscle contraction, the prosthesis will move slow. And if you give it a larger muscle contraction, it will move quicker. And so there's this kind of window that we have to find out how good of control an individual has of making, light contractions versus hard contractions. And everybody's a little bit different on that. And if an individual gets better control of being able to have a more of a gradient between, a light contraction to a hard contraction, then they'll actually have more finite control of the prosthesis as far as how quickly or how fast or how slow it actually moves when they're trying to grab something.
Mm-hmm. Yeah, and then so we also have like on the skin. Like I was looking on there's Otto Bock website that have like the really hyper realistic hands from silicone,
Mm-hmm.
right?
Yeah,
and that also just looks incredibly expensive, by the way, and that kind of a thing. And then I'm also looking at this iLim bionic hand, which looks really cool, but doesn't really look human like. I mean, is that something that people really kind of have a preference for one of those? They want
So,
something that like absolutely looks like a hand, or they're caring more about function or stuff like that.
yeah, and that's one of the critical questions that you have to ask a patient at the onset. I always like to give them a scale from 1 to 10, with 1 being appearance and 10 being function. Where would you put yourself on that scale? And so, once I get that information from them, then I can kind of direct them towards what options, meet those needs that they have. But the one thing to take away from this is that there's not a single prosthesis that's going to make up for all of the deficits associated with upper limb loss. That's a quote from my boss, Tom Passera, that he wrote an article back in many years ago talking specifically about these functional silicone restoration style prostheses. So there's a time and a place for something that is more, functional, and then there's a time and a place that's for something that's has more of an aesthetic appearance to it, and you have to know which type of device to use in which setting.
Yeah, totally. And if we're looking at, like, you did mention like 3D printing, additive manufacturing, is that playing a big role in your work now, or is it just like a tiny little bit?
It's playing an increasing role, because the thing that I love about additive manufacturing is it lets my creativity just go. Because I can do essentially whatever I want with my designs. I'm not constrained by traditional manufacturing methodologies and having to have CNC machines and tooling and things like that. I'm able to integrate componentry that other manufacturers, you mentioned Autobach, and there's Oser and others, that they've already manufactured, and then I can take that part and then design a prosthesis around that part that meets the user's functional needs. So I'm increasingly adopting additive manufacturing more and more. And especially from a cost basis perspective, it allows me to iterate my designs a lot more cost effectively. I think a really good example of this is a prosthesis that I made a couple of years ago using traditional fabrication methods, using wet lamination and using waxes and foams. And this was a prosthesis that was a transradial level prosthesis, and it had a BOA dial system in it that is used. BOAs are like what's on your snowboard boots. You tighten it. It's got a cable, and we use it with panels on the prosthesis to be able to tighten up areas of the prosthesis when a patient wants it. And so I hid this BOA panel behind a door on the prosthesis. And all in all, this prosthesis took me 4 days straight of like 12-hour days of fabrication to make and with using traditional methods. And it ended up being pretty heavy because I had to do 5 different laminations. And every time you do a lamination is where you inject resin into composite materials to create a shell. So I had to do 5 of those in order to get all the features that I needed out of this prosthesis. Well, I was able to redesign that same style of prosthesis for another patient just this past year. And obviously there was a learning curve for me to be able to learn how to do that, but now I know how to. And if I needed to do that in the future, it would take me at most a day to design that same style of prosthesis. And then I can print it out however many times that I want. And if I need to make an adjustment, I can go back into my design, make a quick adjustment, and then send it to the printer again, or just reprint a specific part of that prosthesis that needed to be changed. And ultimately at the end of the day too, that whole prosthesis ended up being lighter weight than any other of the prostheses that I've made in the past with traditional manufacturing. So, it's just awesome. The capabilities that it unlocks, to me as a clinician, because I can just design the prosthesis more specifically to the patient. I mean, additive manufacturing is tailor-made for this. It's low volume, high complexity, and that's exactly what upper extremity prosthetics is all about.
I like this iteration thing. I mean, I think that's ideally something that is ideally suited for this agile engineering of fail, and then keep doing it. And that's we're really good at that.
Yeah. And that's exactly what upper limb prosthetics is about. When done correctly, there is a lot of prototyping done before you get to this final device that actually does what the patient wants. Once again, making that comparison between lower extremity and upper extremity. Lower extremity, you make one test socket that goes over the patient, you check the fit of the socket, make sure it's worked, you connect a foot to it, you have them walk, you align it, and you're ready to make the final device essentially at that point. With upper extremity, you need to fit the socket, make sure it's right, then start to attach some parts to it, then let them go home with it and let them try it out, make sure that it's working for them. They come back, they give you new feedback, you iterate, you change some things out, you change the style of the socket, you send them home again, let them try it out. And, it's a process that takes typically months to actually do properly before you get to the point where you say, okay, we are now ready to take this prototype and turn it to what we would call permanent or a definitive prosthesis that is now going to actually look nice. Because, these prototypes that we send them home with sometimes, there's glue and tape and fiberglass and they're not the nicest looking things, right? But they're functional. They verify the function and the alignment of components, and then we take it and make it look nice. Another cool thing about additive in this whole process and a digital workflow is that you can have them use that device, and then they come back. And if you made that device with, traditional fabrication processes for the prototype, gluing things together and whatnot, you can actually 3D scan that whole device and then digitize it and make it look nice. But you're able to maintain the alignments and the shapes and everything that are critical for the function of the device. So I love that aspect. And my favorite key is, Control Z to be able to undo. You can't with traditional fabrication processes, you get to the end and you can't hit Control Z to undo something if you really didn't like what you just did. But with a digital workflow, you can, and that is my absolute favorite key combination.
So, Chris, do you feel like it saves you time, or is, so many companies say, oh, 3D print because it'll save you time, or do the digital thing because it'll save you time. Is that really what the digital workflow is about, a byproduct, or can you share a little bit about what you've seen just in your practice with that?
Yeah, absolutely. So initially, it's not going to save you any time whatsoever. I'll be straightforward and honest. You have to dedicate a good amount of time to get proficient at it. If you, as the clinician, are going to be the one who is designing these devices. Now, if you decide to hire somebody into your clinic who is already proficient in 3D modeling and scanning and whatnot, then you can get up and running a little bit quicker, I think. But if say you own your own practice and it's just you and maybe a couple of other clinicians, you're going to have to dedicate some nights and weekends to learning the technology before you're going to really see the benefits from it. But once you do start to see those benefits, after a period of time, I feel like the savings starts to become exponential because you realize, how you can save on materials, how you can save on fabrication time, how you can save on potentially, your technician, your traditional O&P technician who's used to working with their hands now needs to become a digital technician who's used to working with a computer to produce, the products that we're fitting on our patients. So it is a transition, but I think it's a transition that's well worthwhile. From a cost savings perspective, when you think about, what it costs, if you were to pay somebody else to make a prosthesis for you, depending on, what type of prosthesis it is, it's going to cost a couple of $1,000s potentially for them to fabricate that for you. With 3D printing, it allows you to, at least have, if not quarter that cost when you're actually talking about the actual printing of the device and the fabrication and final assembly. It can be significantly less expensive in that regard. HP multi-jet fusion technology has allowed us to be able to truly 3D print parts that we feel comfortable sending out the door as a definitive device. Whereas in the past with just FDM style printers, really I didn't personally ever feel comfortable sending that out the door as a finished product for the most part. There's a few exceptions to that, but in general, especially when you're talking about the types of printers that you could buy fairly inexpensively, the quality that comes off of those devices just for me did not meet my expectations for a finished product. But now with HP multi-jet fusion, and being able to send your designs off to a service bureau to have them print them, and then they mail them back to you and you do the final assembly. I mean, it really is a very cost-effective and cost savings method of moving forward in this profession.
Yeah, but do you have printers in your workshop as well, or?
I do. Yeah. I mean, I have an FDM printer in my office, and we use that a lot of the time for prototyping, and designing, custom components, and then, iterating that design a couple of times. And then once we like it, then we can send it off to have the definitive made on a different style of printer. But it allows me close at home to be able to monitor and iterate quickly without having to wait for the shipping times between somewhere else. So I think it's beneficial to have a basic printer on site. Not only that, it just helps you better understand what additive manufacturing is all about, and helps you conceptualize what you can do and what you can't do.
No, definitely. And what kind of materials do you like using for like, let's say, for either your prototypes or your final devices?
With additive manufacturing specifically, or just in general?
Sorry.
Yeah. So, I mean, I print a lot of things in PLA, just, cheap, quick, to prototype and iterate. We will use PETG a lot for our diagnostic sockets because it's somewhat transparent, and so it's really important to be able to, in your diagnostic sockets, see through the plastic so that you can see what sort of pressures you're applying to the individual's limb. So that's really common. If you want something a little bit more robust, we've used Toluene alloy as a material to print, and then for flexibles, TPU, NinjaFlex, those are products that we've used in the past too. And
when you outsource,
when we outsource, for the most part, I'm using PA12 on an HP multi-jet fusion printer. That does a really, really good job for the types of components that we're building for these patients.
Do you finish them as well, or
what's that?
Do they finish them to like vapor smooth them or something? Or
so the Dimension for coloring and then post processing with vapor smoothing is kind of my typical go-to post processing. But you can go well above and beyond that too. You can have them wrapped in vinyl wrap if you want to, or you could make an underlying structure that's just a basic raw finish off of an HP multi-jet fusion printer, and then you can laminate over the top of that too, and using your traditional lamination methods, and make it look however you want, or send it to an auto body shop and have them prime it and paint it for you. I mean, you can finish it however you'd like.
Yeah, but is that because I remember a lower limb there seems to be a lot more like really, really cool like carbon fiber prosthetics and stuff. It's like really in your face, cool, kind of like it's not a bug, it's a feature kind of thing. But in the upper, it seems to be much more that many more people kind of want it to resemble like an arm, or is that just a?
That's not so much the case anymore. Yes, historically it used to be, absolutely, and that was very common. But now in upper extremity as well, it's the paradigm, especially in the United States, has really shifted to more of show off what you've got, and own it, make it your own, and show your personality through your prosthesis. And so that's one of the funnest parts of the whole process too, is like telling your patient, hey, what do you want it to look like? How can we make this be yours? Like what can we do for you for that? And so with our silicone work that we do, we can color the silicone however we want. We can put glitter in it and graphics in it and things like that. We can do that part, and then the frames of the socket. Likewise, we can make them essentially whatever color they want them to be, or whatever design. 3D printing is cool because we can actually make embossed designs in the sockets now too, so that there's actually like a 3-dimensional texture to the device, which you just can't do with traditional manufacturing. So making lattice structures and things like that, it's a whole lot of fun.
Mm-hmm. And do people want like stuff like their sports team or something, or is it really much more personal, or what are people into?
Yeah, sports teams, superheroes, fantasy, or technology. I had one patient who actually took their ILM and they took it to an airbrush artist, and they had them airbrush and make it look even more robotic, like showing all the gears and motors and everything on the back of it. It turned out really cool. So yeah, it's fun.
Have you thought of like letting the people help assemble the thing as well?
I try and make it a point to allow my patients the opportunity to come into my lab and see what the whole process is like and witness it, so that they understand what goes into it. Because admittedly, a lot of the time when they come to the office, there is some downtime when they're sitting around waiting for me to do something, and I like them to know what I'm doing in the back. Generally, when it comes to the final assembly, though, I'm the one who does that because I want to take the liability. I don't want to,
of course, yeah.
shift that on anybody else.
No, I was just thinking that it could be like there's this IKEA effect, right, where you have like much more an ownership feeling of something if you assemble it yourself. Let's say.
Yeah, so
much more affect.
One example of that recently was that I made this. It was a lower limb prosthesis actually, but the patient loves dragons, right? So I spent time with him online looking for designs of dragons, and then in this case, to put that design on the prosthesis, I used a vinyl cutter to cut a vinyl sticker. And so then I printed or cut out a couple of these different stickers and showed them to him, and we looked at the placement and where we wanted on the prosthesis, and then once he settled in on the design, then I made it for him. And that's kind of everything is bespoke. It's tailor made to the individual, and so I like to give them that experience of kind of like it's a bespoke suit that they're getting to pick out all the different functions and features of it, because they do own it more when they had that input and involvement.
Okay, yeah. Sounds like a really wonderful approach. Chris, thank you so much for your time today.
My pleasure. Thanks, Joris, for having me, and thanks, Brent, as well, for inviting me on. I really enjoyed speaking to you both today.
Yeah, I liked it. You really enjoyed it too, right, Brent? Or
I think it's great. I mean, I think going back to what Chris was saying is that you can kind of hear his experience kind of come through, right? So like he sees a lot of these upper extremity prostheses, and I think this is where it's important to separate kind of like the toy prostheses from the professional prostheses, essentially. And you want to go to Chris, who has done many, many, many devices and thinks in the way he does and uses the tools the way he does to get an upper extremity prosthesis, somebody that's specialized. And so I appreciate letting us into that world.
Yeah, definitely.
My pleasure.
Definitely. And yeah, thank you very much for listening. This is a wonderful episode once again. And thank you all for being part of the Prosthetics and Orthotics podcast. Have a great day.